Okay, so I'm going to give yet a fourth characterization of cofibrations, and this one's called a neighborhood deformation retract. Deformation. Okay, so given a cofibration, right? This is equivalent, so this being a cofibration is equivalent to, so let's draw a closed set here, A in X, and then I'll have some U that I can pull in. So the idea is that you can kind of pull in neighborhoods. And so the main application for me, why I care, is that in the mapping cylinder, okay, so we have this thing here, like so. So here's X down below, right? Okay, so here's A cross I. This is one of the pictures of the mapping cylinder. The other picture we draw is that boxy one. Here's X. So here, if we kind of just take this neighborhood here, this can retract onto this piece here, right? And so this shows us that the mapping of A, so A goes into, so we have A in here, it goes into here by the inclusion at 0. So here's the point 1. And then in the other picture, we'll reverse 0 and 1. But so we draw it like this. And then here is A goes into this thing here. And actually, this works for any, this works for any map, right? It doesn't need to be a cofibration. But this inclusion here is a cofibration. So this is a cofibration. Because we'll be able to do a neighborhood deformation retract of this top piece. Okay, that's the idea. And all right, so we can always factor every morphism into a cofibration followed by a deformation equivalence. Okay, so I said what I want to do, and so now let me get into the nuts and bolts of it. So what is a neighborhood deformation retract? So it's like a time function that allows you, so let me give a definition. So a neighborhood deformation retract is a pair. So what we'll have is we'll have a time function, right? And we'll have a homotopy, right? Where this thing here, tie. So this is kind of like a distance function to A. Okay, H. Right. So this is from X cross I to X. So this is a deformation of the identity. So this is like kind of like a time or a distance to A. And then this thing here is, this is a homotopy of the identity. I mean, I guess this is really the neighborhood deformation retract, right? This is really well, of the identity on X. Okay, and so let me say more precisely what these conditions are. So the conditions are that that tau of X is 0 if and only if X is in A. So we'll have that here, that H0 is the identity on X, and that HT relative to A, right, is the identity on A. So it fixes A, and at the bottom it fixes. So it just kind of pulls things into A, and once it's in A, it gets fixed. And then the other thing is the time, how these two things are related. So they need to be coupled, right? So in a definition, with two things, they better not be independent, right? And so it says that this thing here is an element of A. And furthermore, I mean, I guess I could have written it like this. This is maybe a slicker way of writing it. In just one swoop, we can say h of xt is an A when t, let's say t is greater than or equal to tau of x. So when you're at that hitting time, right, then this thing is going to be in A. So it's gonna retract to A. Okay, so those are the conditions that we have. And so a consequence of these definitions, the immediate consequence is that, so maybe I can put this here. Well, maybe I can put it here. Okay, so the consequence is the neighborhood deformation retract. So here's my neighborhood. So take U to be the set of X. So this is a continuous map, of course. Right? These are both continuous, where tau of X is less than 1. So if there's like a finite, so this is like the set of X such that there's a finite hitting time on the on this homotopy, right? Then H1 of U, right? This is equal to A. Okay, so this neighborhood retracts onto here. And so at 1, it's a retract of the neighborhood. Okay? H is a retract of the neighborhood. Okay? And so the theorem that I want to say is the following. The theorem is that here, this is a cofibration, if and only if there exists some tau h, a neighborhood deformation retract of A. Okay, so all right, so let me kind of say a little bit more about this. So I can say how to construct it, but maybe maybe I can say, okay, so maybe I'll draw make a drawing. Okay, so here's the drawing. Well, okay. So let me define. I'm only going to give part of the proof. So proof. And I'm going to show that that this thing here, so the neighborhood deformation retract, implies that it's a cofibration. Okay, and so what we'll do is we're going to show we're going to exhibit a contraction here. Oh, sorry, like this. So this is X cross A to. Then this is an excuse me. So this is the mapping cylinder I, and so this is with the arrows reversed. So this is maybe so this is X cross 0, and this is A cross I. Sorry, this is A cross. This is X cross I, like so. Okay, so we need to show that there's a retraction like this. Okay. So that's what we want to do. So we need this. Okay, so how are we going to do this? I'm going to define a map. Okay, and the map, and so let me kind of draw this thing here in a different way. So here's I, right? And then here is X. Okay, here's I and here's X. And so this is a time here. And then we have this time function. So here's A. A is, let's say A is the subspace up to here. Okay, and then we have this time function. And maybe it hits 1 over here. Okay, so and so this is the if this is the t-axis, this is t is equal to tau of x. Okay, and And so at some, so what's going to happen here? So, so we're going to use the h. Okay, so now let me define the function. Okay, so this kind of breaks this x part into two pieces. So after it's here, it'll be fixed, right? And I need to define a retraction onto this piece. So what we want is we want to define a retraction onto, this box plus this line. Okay, and here's how we're going to do it. So we're going to define h tilde of xt. Okay, so if it's going to hit, then we're just going to let it be that piece. So it's going to be h of xt, okay, times t minus tau of x. Excuse me. If t is greater than tau of x. Okay, and so when t is greater than tau of x, this thing goes in here. And then there's a little height here. Okay? So what happens is what happens is all these little points, so this is in this region. So this is the t greater than tau of x region. And then here, all of these things, so the difference here, so we take a point and we look at the height difference here, that's here. And then it gets mapped to, wherever it gets mapped to in h of x, so it'll go something like this. So all the points that are a certain distance away, they get mapped here, okay, into this region. I'm drawing it close because there needs to be some continuity here. What we'll do here is when t is less than or equal to tau of x, we'll have a map like so. So we'll have h of x. We'll just do this one, h of xt, and then we'll put 0 here. Okay, so below this line, it's going to hit down here somewhere. So things that are below, right, are going to hit down here. Okay, and this whole thing eventually retracts, right? So the things up here will be more solidly inside of this, and the things down here will be more solidly in here. But so this is what the map h tilde looks like. I'm drawing it as kind of a flow, but really it's just one map, and it takes this point to this point, right? There's no real continuity here. Okay, and so this defines the retraction. Okay, and so that is all I want to say about that. Really, the converse, the idea of the converse is kind of to take a homotopy and then define some sort of minimal distance to A. Okay, so and that's all I'm going to say about that.